So in this video, we'll start describing the snake level. Okay, so this will help us. This is one of the key ingredients in proving the Meyer-Vietoris theorem, which, as we've mentioned, is a kind of key tool for calculating homology groups. So we're going to suppose we've got some chain complexes, U star, V star, W star, and some chain maps, I and P between them. Okay. And I'm going to assume that they give me a short exact sequence at each in each degree. Okay. So remember, these are chain maps, which means that DI is ID, DP is PD. Commute with the differentials in the chain complexes, and then it's going to be short exact. So that means that I is injective, and P is surjective, and that the image of I is the same as the kernel of P. Okay. Then the claim is that there are natural maps, delta. So this is going to go from nth homology of W back to the n minus first homology of U. Okay, so we're kind of going from W back round to U, but shifting dimensions down by 1. Such that if we do so we've got an Hn plus 1 of W, then we do a delta to Hn of U, then you do your I lower star to HNV, and then P lower star to HNW, and then you do delta again to Hn minus 1U. Well, it's going to be exact for all that. Okay, so the idea here, because I and P is short exact, it seems reasonable that maybe I star and P star should be exact, or maybe even short exact. And in fact, it is I star, P star, that is exact, but I star is not injective in general, P star is not surjective in general. So I couldn't put a 0 here and still be an exact sequence, or don't get a short exact sequence in the middle. So I star is not injective. It has a non-zero kernel, but the kernel is just the image of this delta, and then the kernel of delta is the image of image of P lower star. So everything kind of meshes together. So this is what we need to prove. The first point is just we need to define this map delta, which takes some work. Let's just say again what we had. So we need to define this delta from HNW to Hn minus 1U. So our kind of first attempt, as it were, is that delta is I inverse dP inverse. Okay. This is not really much of an attempt. What does it even mean? I mean, P is not an isomorphism, so what's P inverse? And then I is not an isomorphism either, and so doesn't quite make sense, but it's kind of an initial indication what we're supposed to do. So the second attempt. So given some W bar in HNW, then W bar is square bracket W for some W. And then we choose V with PV is W. In other words, V is kind of a choice of P inverse W. Then I want to choose U with I of U is dV. Okay, so in other words, U is a choice of I inverse dV or I inverse dP inverse W. And then I want to define delta of W bar is the corresponding homology class. And let's just actually draw a little picture of that. So we've got UN here, Vn here, Wn here, and then one dimension down, Un minus 1, Vn minus 1, Wn minus 1. And so we've got these Ds like this. I and P, I and P. And so we kind of had our W here, and then we chose a V here that goes there, and then we've got D of V here, and then we chose our U that goes like this. So that's how this procedure works. But this is not really a very good definition either. Firstly, how do we know that there exists such a V? And given that, how do we know that there exists such a U? And if we want to write this square bracket U, then U had better be a cycle. So we need to check that du is 0. And then even if we've done all those things, we made some choices along the way. And how do we know that the final answer doesn't depend on those choices? There's a whole bunch of things to check. And turns out in order to check all those things in a coherent way, it's best to sort of proceed in a slightly different way and study the set of all possible choices that we could make in here and see what the structure of that set is. So that's what we'll do. So here's the key definition. Okay, let's just draw up here the context again. So a snake is a list like this: W bar, W, V, U, U bar. Firstly, W bar is an element of HNW, which remember is the same as ZNW mod BNW. And then secondly, W is in Wn with dW equals 0, or in other words, W is in ZNW, and the corresponding homology class is the W bar. Thirdly, V has to lie in Vn with PV equal W. Fourthly, Z is in UN minus 1 with du equal W. In other words, Z is a n minus 1 cycle for U. And and then I of U is supposed to be the same as dV. And fifthly, U bar is the homology class corresponding to U in the n minus first homology of U. So again, we can show where all these things lie. Here you've got your W, your V, your dV is IU, your U here. And then then you've got your U bar and your V bar, which correspond to this W and this U there. And so we're going to prove two lemmas. So firstly, for any W bar, there's a snake starting with W bar. And secondly, if they start with the same W bar, then they end with the same U bar. Okay. So if we assume all this, then we can define delta W bar is the end of any snake starting with W bar. Right? So lemma A says that there is such a snake. Lemma B says that any two such snakes have the same endpoint, so it's well defined. This is a well-defined rule for giving you your delta. So that'll be so we'll prove lemma A and B in the next video.